All right. So we are going to see our first clustering method for which can be used to cluster microarray data, and this is k-means clustering, and it's one of the simplest clustering methods. And the algorithm is really simple to implement, but there are different variations. When you see k-means clustering in different places, you will see. You're going to see in some of them, for example, the initial clusters may be chosen differently, or how empty clusters are treated, how you compute the representative for a cluster, the central for the computing the mean or of the clusters. Some, for example, there's a k-medioid algorithm in which instead of using the average of objects that fall into a cluster, they use the median of the objects that fall into a cluster. Now, maybe probably to reduce the effect of outliers and such. So the idea is, as I said, it's really simple. The only parameter it has, I mean, it says the distance measure, Euclidean, Pearson correlation, whatever it's going to be, it's a parameter to many clustering algorithms by default. So after you decide on some distance measure that can measure distances or similarities between two objects that among your set of objects, the other parameter that is specific to k-means is the k, which is the number of clusters that you want to divide these groups into. It partitions the original data set into k different partitions, not overlapping. Again, some variations of k-means, like fuzzy k-means or fuzzy c-means, allow some same object to be a member of multiple clusters at the same time with some probability. But in the original version, where we have just each object belong to a particular cluster. So let me try to talk about this here on this slide. For example, we may have some objects which are points in 2D. Let me try to show you how in 2D k-means is going to work. For example, we may want to cluster these two sets of objects into two. So when k is equal to 2, we try to group these objects into two groups such that close by objects tend to appear in the same cluster, in the same group. Our goal is to get intra-cluster distances as small as possible and inter-cluster distances as far away as possible. So there are different measures to show, to measure how a final clustering is good. Some indices, for example, Dunn index, or different measures that show whether a clustering is good or not. And one thing, as I said, one thing that is used is our goal intuitively is if certain objects are in the same cluster, we want them close to each other, as close as possible. And if two objects are in different clusters, we want their distances to be as large as possible. Okay. So, for example, if you want to divide these two sets of points into two groups, I can just by looking at this data set, I can see maybe this can be in a group and this can be in another group. I mean, these points. Okay, so the result of a k-means clustering may be this. These 4 points are in cluster 1 and these 6 points are in cluster 2. But how do we do that when we're just given the points like this? And don't forget that we try to do this in a higher dimensional space. If you're just in 2-dimensional space like this with these points, you don't need to have these complicated clustering algorithms to run on your data. You can just plot your data and visually cluster them on your own. So manual clustering by just looking at them visually on a 2D plane is really easy. The difficulty arises when your objects are higher dimensional. Try to group objects that are 10-dimensional, 20-dimensional vectors. Okay, and if you want to sample our genes, for example, each of them will be, in this example that I have showed you, there were 118 samples. So each gene, for example, gene 1, is going to be a vector of expression values in which, for example, expression value in sample 1, expression value in sample 2, and expression value in some sample 118. So each gene, as you can see, is a point in 118 dimensional space. These are, it's like X, Y, Z, W, all 118 different coordinates. And here is another gene, is another point in this high dimensional space. And you will not be able to visualize them nicely on a 2D plane like this when you have higher dimensional object. The only thing that k-mean is going to have to run will be those vectors and the distances between two things. For example, the distances, how do you compute the distance between 2 points in this high dimensional space? Do you use Pearson correlation or Euclidean distance? All right, so this is how k-means is going to work. So let's start with the first step. Since we are going to, k is given as a parameter to the algorithm, which is considered one of the disadvantages of k-means algorithm. Because if you have, for example, if you want to group the genes into clusters, how many clusters you should have to group the genes? I mean, is 4 good or 5? How many natural clusters are there in the genes, in the set of genes? 6, 10? So most of the time, you don't know what k is beforehand. In the case of samples, for example, we have that metadata, or if you're comparing two samples with each other, for example, normal and disease samples, you know that k is equal to 2. So in certain situations, k is naturally given by the problem to you, but sometimes you don't know what k is. And many people, when they're running their algorithm, they run the same algorithm for different values of k, k2, 3, 4, and go on like this until, for example, the cluster result, the final clustering looks very bad, or choose the k which gives you best clustering. When I say best clustering, we need to have, as I said, that those kind of done index or other measures that shows whether a clustering is good or not. Intra-cluster, clusters, distances within the clusters as small as possible, distances between clusters as large as possible. So the first step of k-means is initialize. The idea is the algorithm is very similar to expectation maximization type of algorithms, in which we first fix something in an iteration. It's an iterative algorithm, and the iteration goes until convergence. So the convergence here means that nothing is changed between two iterations, and if you continue doing the same thing over and over again, you're going to be just, you're not going to be making any changes. The clusters are going to remain the same, the cluster centers are going to remain the same, whatever you do in the subsequent iterations. So until convergence, this is what we're going to do. We first need some cluster centers. So k means that mean in the name of the algorithm denotes the center of a cluster, which is computed as an average of its group members. Initially, since no point is assigned to any one of those clusters, we're just going to assign some cluster centers randomly. What you may have is these cluster centers, which are like virtual points in your space, okay, could be chosen as some random points in two different parts of your space. Okay, for example, this may indicate, the cross may indicate cluster 1, and this plus sign may indicate cluster 2. So the first step is randomly get some clusters like this. One way to do is just generate some random point in your space for your cluster 1 and cluster 2. But when you do that randomly, it may turn out they may turn out to be very close to each other. For example, what if this is cluster 1, this is cluster 2? When you do it randomly, they may end up being like this. All right. Or a more intelligent way to initialize cluster centers would be to get from two different ends of the, just select them so that they're far away from each other. For example, cluster 1 here, cluster 2 here. And another variation is that the first cluster and the second cluster, cluster 1 and cluster 2 centers, at the first step are chosen from the available points randomly. For example, this is cluster 1, this is cluster 2. So we may choose 2 points randomly from our data set to be representative cluster centers in the first iteration. Okay, so these are all different variations that exist in how k-means is implemented in practice. Okay, let's do that actually. Let's choose among the set of points. So let's see what kind of a variation I have. So randomly assign k points to k clusters. So it doesn't talk about how this random k clusters are specified in the first iteration. So let me, actually I can close this off, I will not need this. Yeah, let me quit this one. All right. Now, I will just start with, this is cluster 1, this is cluster 2. All right. This is, in that iteration, this is what I'm going to do. In every iteration, actually, after the cluster centers are identified, at every iteration, my goal will be this. Assign each of the points to their respective clusters. And how do you assign a point to a cluster? You compute its distance to the cluster centers. Since cluster centers are like virtual points, they will be represented as a d-dimensional vector, the cluster center that corresponds to cluster 1, cluster 2. So you compute 2 distances for each point. For each point, if k is equal to 2, you compute 2 distances, but if k is k in general, you compute k distances. For each object in your data set, you compute k distances to all the cluster centers. And the cluster argmin, the cluster which minimizes this distance, the distance between object I and cluster k, so the one that minimizes this distance, the value of k, the cluster ID that minimizes the distance between your object and all of the clusters, it becomes, you assign that k to be the cluster of this object I. Okay, so in other words, it's just a simple greedy mechanism. Whichever cluster is closest to this object, you assign that object to that cluster. So let's try to do that in this data set. So for this one, this seems to be closer. By the way, I'm going to use the green color for the second cluster and red color for the first cluster. So let's try to assign objects to their clusters. Yeah, let's give this one, although this looks like equal, let's give this one to the green one. This is also green, but all the others, I mean, the way we choose this, many of them are going to be like probably, or even this one. Let's give it to this one. It may be, in the first iteration, it may be so bad that, I mean, your original clusters, I mean, the point itself is going to be in the same cluster, the point that was chosen to represent the green one, because its distance to itself is going to be 0. But all the others are closer to this one. This was our cluster 1 for initially, and this was our cluster 2 initially. And it may turn out that all the points are closer to cluster 1. That's okay. But here's what we are going to do at the end of first iteration. We are going to since the cluster 1 now contains many points, as you can see here, its cluster center is no longer here. At the end of each iteration, we update cluster centers based on the current memberships. First, when the clusters were specified, in the first iteration, we assigned each of the points to a particular cluster based on their closest distance, based on those distances. After all of the assignments are made, cluster memberships may change, which is going to change the cluster center to a different location. Cluster centers in the original k-means algorithm, the cluster center is computed as the average, unweighted, just a regular average of all the points that belong to that cluster. So when we take that average, cluster center for 1 may end up being here. Okay? So let me undo all these markings, but I know which ones are which. So what I'm going to do is, here the cluster center 1 is going to come somewhere here, okay? And cluster center 2, since it contains only 1 point, okay, its average is going to still be this point. So cluster 2, now at the end of iteration 1, cluster 1 center became this point here, okay? And cluster 2 remained the same. Now, what will happen in the second iteration is that, again, each point is going to ask which cluster is closest to. This one, this one, this one, cluster 1, cluster 1. This one may still be cluster 1, cluster 1. But these 3 are now nicely going to say that, oh, okay, we are far away to this cluster 1. We are closer to, we just figured out that after the clusters change, these 3 have figured out that they're closer to cluster 2, and they, as you can see, the cluster memberships changed in the second iteration. When cluster membership change, what will change? Cluster centers. So the new cluster center in the third iteration, at the beginning of the third iteration, probably is going to be somewhere here for cluster 2, or maybe somewhere here. I don't know. Maybe, yeah, somewhere here. Maybe you just take these 4 points, take their average, that becomes your new cluster 2 center. It's not, as you can see, it's not one of those 4 points. It's just the center. Let me indicate the center with a special symbol like a circle around it to indicate that it's not an actual point, but it's the cluster center. Okay? And since these 3, which were before a member of cluster 1, they now members of cluster 2, this first cluster center may also shift a little bit to the left like this. The new cluster center at the beginning of the third iteration may become this. Since the cluster center changed in the fourth iteration, this point, which was the original cluster 1 point, that was the original point that we selected as cluster 1, if you remember, it's going to now, as you can see, is closer to this cluster 2. At the beginning of the third iteration, it may say, oh, I'm a member of cluster 2. This will say, I'm a member of cluster 2 as well. And cluster 1 then, in the fourth iteration, after it's updated, it's going to move a little bit again to the left here. But after some point, you're going to see that between 2 consecutive iterations, the cluster membership, maybe at the beginning of fourth iteration, these 4 points are going to say, oh, we belong to this cluster. These 6 points are going to say we belong to this cluster. These 4 points are going to remain as in their clusters. No change. No change in cluster membership means that the cluster centers, when you take the average again, they don't change. Okay, so it's going to converge. It's going to remain the same like this onwards from iteration 4. Therefore, we stop at iteration 4. And at this point, we have nicely our clusters separated into 2 groups, as you can see, which was the original grouping. So this was, even if we started at bad initial random points, k-means clustering, this modification of the cluster center at the end of each iteration, may help resolve the clusterings, get to the natural clusterings, if there are really some natural clusterings within your data. Okay, and if we try to divide the same data set into 3 groups, k-means will still work. It will try to make it into 3 clusters or 4 clusters, but the idea is just at each iteration, so here the algorithm, assign each point to its closest, nearest cluster, and use the centroid of clusters to compute the distance to a point. So it's always between 2 points when we compute that cluster. Whether it's Euclidean or Pearson correlation coefficient, we use this cluster center as a virtual point to compute this distance. After all points are assigned to clusters, we compute new centroids, new centers of clusters based on these new memberships, and then we then reassign all points to the cluster. So this is just done iteratively over and over again until cluster membership do not change. There are different k-means demonstration on the web that you can find out, but I think this example on this whiteboard was clear enough for you to understand the method, but you may also experiment with some points that you may plot and see how k-means are going to behave in those settings. K-means has one problem, which is here empty cluster example. Let me show you this one. Sometimes when you have a certain k is equal to 3, for example, you want to partition your samples into 3 groups. But what happens, or is it possible, let me ask you, in certain iteration, the points are assigned to 2 of those 3 clusters. What if one cluster has no points assigned to it at the end of some iteration? It may, or is it possible? And if such a case happens, what are we going to do? Well, what I mean is that if we want to say, I want to have k is equal to 3, I want to see 3 groups, but with certain luck, you may end up with 2 groups at the end. There's this empty cluster problem, and this one shows how it's possible. So this is, there are 2 natural groupings in the data, as you can see, the square and the circles. There are 2 natural groupings, but what if we want to group them into 3? We may not know this natural grouping beforehand. Let's try to group these points, these 7 points, into 3 groups. Let's try to do it in 3 groups. And here are our random initial cluster centers. This is the red one, the blue one, the green one. And these random cluster centers are like this. And at the end of this iteration, the blue may say I'm closer to the red cluster center, and this other blue may say I'm closer to this green cluster center, and nobody may want to be in this blue center, or this virtual center. So it may be the case that at the end of the second iteration, we may end up with a situation like this: 0 elements in our cluster. Therefore, when you're implementing this k-means, you have to be careful about computing the centroids. If a centroid contains 0 elements in it, you may get a runtime error saying that division by 0. If you try to recompute the centroid for the blue cluster, which may give you divide by 0. If you just add all the cluster points and divide them by their number to find the average, it will be 0 in this case. So you'll get a division by 0 runtime error. So you have to be careful about how many elements each cluster have at the end of each iteration. So what do we do in this case? We may just then remove this. We may reduce the number of k to 2 and remove this cluster completely and continue like this in our algorithm. So there are different ways to resolve this issue, but just that's one of the issues that you may face when you use k-means clustering. Any questions about k-means clustering? Yeah, okay. I'm going to continue with self-organizing maps. I'm going to skip this hierarchical clustering part because we have already seen neighbor joining and UPGMA as hierarchical clustering algorithms. In the most general version of hierarchical clustering, there are different ways of how you compute distances between 2 clusters. In UPGMA, for example, the distances, when we update our distance matrix after each iteration, we were using the average distance between members. Neighbor joining was using something else. It was using distances on the tree to compute distances between 2 clusters. But In general, there are different ways, different strategies to compute distance between two clusters. The average linkage clustering is similar to what UPGMA uses, but there are two other strategies to compute distances between two clusters. Single linkage computes the distance between two clusters by using their closest members as the distance between two clusters. Complete linkage, on the other hand, defines the distance between two clusters as the farthest distance between two cluster members. So the figure is like this. If this is cluster A, this is cluster B, the distance between two such big clusters can be either defined like this in single linkage or like this if you're using complete linkage clustering. In average linkage clustering, it's the average distance between all cluster member, and UPGMA and neighbor joining uses something similar to this. But just know these terms too. When you see single linkage or complete linkage, when you're using those array analysis tools, microarray analysis tools, this is what those terms mean. All right. So, and hierarchical clustering gives you a hierarchical grouping of your objects, which are called dendrograms. You may cluster samples or you may cluster your genes. And if you have nice clean data, for example, you're just using this differential express genes, you will probably most of the time get a good grouping like this. All downregulated genes in one cluster, all upregulated genes in the other cluster. You can cut this dendrogram at any level to get different numbers of clusters with different granularity. Okay, so this is another example showing the clustering. And the final algorithm that I'm going to discuss in this chapter is self-organizing maps. And the self-organizing maps clustering, it's considered like a clustering algorithm. And it also has many different variations. But it was originally developed for visualization purposes, just like PCA, principal component analysis. Its main purpose is to reduce the dimension, higher dimensional data onto 2 dimensions. How can we visualize high dimensional data on the plane? That map is what map is that 2-dimensional visualization playground that we have, and the goal is to put high-dimensional objects onto a 2D map so that similar objects are placed on nearby locations on the map, and faraway objects in that and when I say nearby objects, faraway objects, I refer to the distance that you compute in that high-dimensional space. Again, we have to use either Euclidean distance or Pearson correlation coefficient or some other distance. We need to have a way to measure the distance between 2 objects in the high-dimensional space. And based on that distance in the high-dimensional space, our goal is to map them onto a 2-dimensional. It's like if you want to project them on 2 dimensions. Far away objects, I want them far away on this 2D map, and close objects in high dimensions, I want them close to each other in this 2-dimensional map. That's the intuition behind self-organizing map, and try to then show similarities and differences between many objects from your data set on this 2D map. Self-organizing maps are also used for clustering purposes when the resolution of the map that you're mapping on is small. If you use, for example, a 3x3 map with 9 pixels only, each pixel may correspond to a particular cluster. And when I say 2 objects fall on nearby locations, if you're using self-organizing map for clustering, actually it will mean that 2 objects fall onto the same pixel. The nearness will mean falling onto the same pixel. But in general, when you have a higher resolution self-organizing map, for example, a 500 by 500 map, your goal would not be just to, so 500 by 500, that's 25,000, right? Uh, yeah, 25, actually 250,000. 500 by 500 map, 250,000 pixels. Your goal is not to create 250,000 different clusters. In that high resolution self-organizing map of 500 by 500, you would want to have similar objects that are in the high dimensions to fall in nearby places on the map. But these different variations of self-organizing maps may use different resolutions of those maps in which a single pixel may be considered a cluster. I'm going to show the higher resolution version, and hopefully the method is going to be clear with these examples. So it was proposed by Kohonen, who is a person in computer vision too. So he or also neural networks, artificial neural networks. Kohonen networks are well known. So therefore, the self-organizing maps have also similarities to neural networks, artificial neural networks as well. Some of them, some people do not call those pixels, the locations on the map. Sometimes they are referred to as neurons, but I will call them pixels in this presentation. So it's basically a dimensionality reduction, a way of projecting higher dimensional data onto a 2D map. So we cannot visualize high dimensional data. If it's more than 3 dimensions, you cannot view it on effectively as is, in other words. Therefore, we need techniques to visualize the data on lower dimensions. So the way SOMs go about reducing dimensions by producing a map of usually 1 or 2 dimensions. It's most usually 2 dimensions like this, which plot the similarities of data by grouping similar data items together. So this example that we see here is a grouping of color. Color is actually, the color spaces are usually 3-dimensional, like the RGB color space contains, for each color, there's the red, green, and blue component. We could have viewed the red, green, blue components as 3-dimensional. The color is also viewable in 3 dimensions, but if our goal is to project those 3-dimensional colors onto a 2D map, reduced from 3 to 2, we would have similar looking colors, for example, the shades of purple appearing on similar locations on the map. Here are some important components of self-organizing maps. First of all, the sample data corresponds to the objects, the data points that we want to cluster. For example, you may want to cluster those 118 samples. Okay, 118 samples in our example. These are sample data. There are 118 of them. Each of those 118 samples is a 50-dimensional point, 50,000 dimensional point, because each sample contains 50,000 transcript expression in them. So they may be considered really high dimensional, 50,000 dimensional of data points in a very high dimensional space. Okay, in this case, our sample size is 118. If we want to, or if you want to cluster genes, sample size would be 50,000, and the number of dimensions will be 118 in that case. So they are represented by n-dimensional vectors. So here are some sample data that we may want to cluster. For example, as I said, we may want to cluster colors, which are 3-dimensional objects if we are in a 3-dimensional colors, if you're using a 3-dimensional color space like the RGB color space. And this may be my sample data. I may want to cluster these 6 colors to show which colors are similar to each other. All right, or we may want to cluster people, students. We may want to characterize 400 students in the computer engineering department are there different groups of students with respect to their similarities? Like, for example, an example representation in this high dimensional space, maybe 100-dimensional vector. I cannot think of 100 different characteristics for a student, but it may be all the grades that they take from different courses. Some of them may be missing data, but age, gender, height, weight, hair color, eye color, cumulative GPA, interests, social interests, different things. So these may be the feature vector for a single student may be used to represent that student in a 100-dimensional space as a single point. Now, so we have the data, and the main component of the self-organizing map is the map itself. And the map is usually laid out in a rectangular fashion like this, where pixels are also rectangular. There are different variations of self-organizing maps in which the map itself may be spherical or circular, in which the pixels may be hexagonal shapes or some other shapes that a certain neighborhood is defined. Hexagons are good because the neighborhoods of hexagons is well defined. There's edge-based neighbor, an hexagon, if it was all pixels that were hexagons, its neighbors will be the neighbor of a particular hexagon, and they will be sharing an edge. But when you have rectangular pixels like this, another parameter you may want to decide is that, are you going to consider 4 neighborhoods? I mean, are these two west, east, north, and south pixels are the only neighbors of this center pixel? 4 neighbors? Or are you going to consider 8 neighborhoods in which these diagonal neighbors, the northwest neighbor, northeast, southeast, southwest neighbor, are you going to consider all these 8 pixels as neighbors? Or how you compute the distance between a certain pixel, how many pixels it is away from this one? Are you going to be using Manhattan distance or some other distance measure? So we have to decide on these things, because given a pixel, we will need to say how far away another pixel is, which are its neighbors, how close these neighbors are. And in that regard, hexagons may be a little bit better than these rectangular pixels, but rectangular pixels work perfectly fine. Each of these pixels, they indicate a virtual data point in our n-dimensional space. So each pixel on the map is associated with an n-dimensional vector. For example, if you want to cluster colors, each pixel, the pixel has an xy location on the map. The pixel has a location on the map. The pixel also will have some associated data with it, which will be the same dimensionality as the data that we want to cluster. If we were to cluster the students example that I gave, which were 100-dimensional, at each pixel, we would store a 100-dimensional vector that represents some virtual random student. Okay, so the pixels have associated data with them. They do not necessarily correspond to the actual data items we want to cluster. They're just random, okay, initially. And they will then be averages of, just like our virtual clusters in k-means, these pixels will have some arbitrary virtual values. The good thing about this example of clustering color in self-organizing map is that we would be readily be able to view the associated data with it by just plotting the pixel with that corresponding color. Depending on what this RGB value is, we can just plot it that way. And when you're looking at self-organizing maps, when you're clustering colors, that's a very widely used example to teach self-organizing maps. The associated data will with those pixels will be really easy to view as different colors on those pixels. If we were looking at another example where we want to cluster, for example, 100-dimensional objects, the associated data with those pixels, 100-dimensional data, you would be showing 100 numbers here, 100 numbers here. It will not be really easy to visualize those pixels. They will just be pixels. They will not. You will not be able to see them directly. You would need something like this to visualize the map. Let me just show you right here at the end. You would be able to visualize them like this if they were 100-dimensional. And this visualization is an interesting visualization which shows even if they were 100-dimensional, we would be able to obtain something like this grayscale view of the self-organizing map, in which if two neighbor pixels have similar 100-dimensional values, we would they will be whitish, but if it is different from its neighborhood, we are going to represent it as a darker color. Okay, so therefore the boundaries between pixel values will be indicated by these dark valleys that you see here, if it was high dimensional. But I'm going to come to the other part, but just know that each pixel, we initialize our map with some random n-dimensional vectors like this for each pixel. All right, these are sometimes called weight vectors or neurons because self-organizing maps are also closely related to artificial neural networks. Here's the algorithm. The algorithm is really intuitive. It's very similar to the idea behind simulated annealing. Simulated annealing is another heuristic search algorithm in high-dimensional spaces. If you may use it as like an optimization algorithm in which you do big jumps in the search space in the early iterations, and as the iterations progress, you reduce the sizes of your jumps and you try to look for better optimal solutions around the local neighborhood. The term annealing is coming from, I think it's material science or material engineering, but it's the blacksmiths, the blacksmiths who forge swords. When they try to make a sword, they have a piece of steel, some metal, in which they heat it to a very high temperature. When the steel or the metal is heated, it has really high temperature. It's easier to mold it to a sword-looking shape. You may make more drastic changes initially, but as the sword is, or as the piece of metal is cooling down, you make little and little changes, just tuning. Final tunings are accomplished on that. This step of changing the material that you are shaping as it's cooling down. You shape it less and less. This process is called annealing. I think materials engineering. So if you look at annealing process, so heat treatment. What are the three stages of? So it's in metallurgy. Is a heat treatment that alters the physical and sometimes chemical properties of a material to increase its ductility and reduce its hardness. So you heat it to make it less hard, so you make modifications to its shape. It make it more workable. It involves heating a material above its crystallization temperature, maintaining a suitable temperature for an appropriate amount of time, and then cooling. As it's cooling, you make less and less changes. The simulated annealing algorithm does this when you're searching a search space. You make some random searches initially, you make big jumps, and then you start, as the system starts to cool down, you basically simulate that cooling down process by reducing your jump size at every iteration. It's very similar. The self-organizing map algorithm has the very similar idea. We initialize the map with some random color, and for a certain fixed number of iterations, let's say for t is equal to from 0 to 1. So this t is some real valued number. If you're going to run your self-organizing map for 1,000 iterations, you fix the number of iterations beforehand. In certain variations, the number of iterations is not fixed, but in many that I've seen, the number of iterations is a parameter to the algorithm. For example, if you want to run for 1,000 iterations, you change t from 0 to 1 at each step. At the end of each step, you increase t a small amount. If you want to have 1000 iterations, it has to be 0.001. So you add 0.001 to t at every iteration, and t ranges from 0 to 1 in regular intervals in 1000 iterations. Okay, but based on the value of t, you're going to do something different at each iteration, and like simulated annealing, in smaller values of t, you're going to update your map a lot. But as t becomes large values, the update on the map is going to be smaller and smaller and smaller. And the map is going to converge it to some view. Here, the idea is we randomly select a sample from our objects that we want to cluster. And we do this random selection of sample with replacement. Imagine I want to cluster 118 samples that I had in my microarray data. In 1000 iterations, selecting 118 samples, each sample is going to be selected many times. Okay, this is reasonable. But each time we randomly select the sample. It's also possible with very small probability that a certain sample in your objects to cluster is never selected, is never treated at all during the running of the self-organizing maps algorithm, but it's very low probability. We usually have a large number of iterations, and we most of the time each object is going to be selected at least once. So in the second step, we get the best matching pixel to the selected sample. All right. So we look at, depending on if your resolution of the self-organizing map is large, it means that in the second step, you compute the distance of your object to many, many pixels. If it's a 500 by 500 image, 500 by 500, it's 25 and 4 zeros, 250,000. You compute the distance between your selected data point with those 250,000 pixels one by one. So this step may be very time consuming. So you may think about reducing your self-organizing map resolution if it's taking too much time. All right. But out of those 250,000 pixels, we are going to find the pixel which is closest in terms of distance to our selected sample. So it's something like this. If you're clustering colors, there may be different colors all around the place. Red, green, blue, yellow. So you select a color to cluster. If it's a shade of yellow, what you would do is you will just look at this map and it will find the yellow that matches our selected yellow best. And after we select this pixel, the object that we selected modifies the map. It makes the surrounding area and the selected sample close to itself. So that object is like a color bomb dropped to that location on the map. The neighboring pixels, which may not be of the shade of yellow here, but they will be a combination of the selected object and whatever older pixel value they have. So initially in the early iterations, there are big drastic changes made on the map, meaning that the dropped color bump or dropped d-dimensional vector at this location, it modifies the entire content of the pixel that it drops, and the neighborhood that it affects is large. As the iterations progress, you may say, for example, the best matching pixel is not directly replaced by the object. It's a combination of the previous pixel and this one. And as this t gets larger, maybe the drop thing doesn't change it at all. When t is equal to 1, for example, the map is going to stay stable after that point. This is how we simulate convergence. So this is the updated values of this best pixel and its neighbors. And the neighborhood may shrink at each iteration, and the best pixel the effect on the best pixel may change. So how do we do that mathematically? It's very simple actually. We will just use a linear combination of the pixel's new value. Here is what we can say. The new pixel value will be computed like this. Current pixel value times t plus sample value, the selected object's value, times 1 minus t. So when t is equal to 0, it means that whatever your selected object that you select from your bag of objects to cluster, it will be, when t is equal to 0, the entire pixel's contents will be replaced with that object's value that you have selected. Because the current pixel value will be multiplied by 0, it will, that yellow that you selected will replace whatever previous yellow it had in that pixel completely. But as, for example, when t is equal to 0.5, when we are in the middle of our iterations, you see that it will be an average of the current pixel value in that map location and our selected pixel value. And as t gets larger, the selected sample is going to have less and less effect. And the neighborhood that we have here may shrink as the iterations progress. So we're out of time. I'm going to continue on a discussion of self-organizing map on Thursday, and we will finish microarray analysis this week. And in the remaining 2 weeks, I'm going to talk about biological networks. I will be happy to answer if you have any questions. I will stop recording now.